Hello, in this video I'd like to talk about the word logic. So there doesn't seem to be a particular name for this logic, but it's very commonly studied, and it looks like this. So we're first going to define a structure. This is the word structure. It's going to be the words on sigma with a bunch of different things that we can talk about in the structure. The first is a binary relation for prefix. We say that x is a prefix of y if y is just the word x with some possibly empty word tacked on to the end. We say that x is equal length to y if these two words have the same length. Then we use these various successor operations. They are unary operations, which means they only take in one input. They take in a word and they tack a particular letter onto the end. And we'll have one of these for each letter in our alphabet. And finally, we have epsilon, which is a constant symbol for the empty word. We don't actually need this, but it's very handy, so I'm going to include it here. Any formula involving this particular constant can be translated into a formula that doesn't involve this constant, that instead has a variable representing the empty word, and then you assert that that variable satisfies the properties that the empty word does. Specifically, I don't know, something like it's the prefix of everything. So this gives us a structure, a collection of things to talk about, and things that we can use to talk about those things. And I guess for the purposes of this video, we'll assume for now that sigma is just the set containing A and B. This kind of falls apart if there's only one letter of the alphabet, and you don't gain anything by having more than two letters in the alphabet. From this base, we can construct logical formulas, and I'd like to be precise about that process. So we'll start off with terms. A term is an expression representing a word, or generally speaking, a term for any structure is an expression representing an element of that structure. So this can either be the constant symbol epsilon representing the empty word, or it could be a variable. We're going to restrict variables to exclusively represent words when we're talking about this logic. So we can't, for instance, talk about numbers, and we can't, for instance, talk about sets of words. We're only allowed to have our variables represent words for the time being. And then finally, if we have a term, we can, of course, construct another term from it by either taking the successor A of that term or the successor B of that term. And so together, from this base and this generating process, we are able to generate all of the terms in this particular logic. And occasionally I'll use shorthand when it's convenient. For instance, I'll use the word AB to represent the expression, the successor B of the successor A of the empty word. But it'll always be in circumstances where it's clear how we can take our shorthand and turn it into pieces of just the original language. There's kind of a balancing process here. When we're using our language, we would like it to have a whole bunch of things in it. We would like to be able to talk about the empty word. We would like to be able to just straightforwardly talk about the word AB. But when we're reasoning about what our logical language is capable of, we'd like our language to be as small as possible, so our proofs are as small as possible. And so very often we'll want to introduce this extra step of having shorthand for various things. This is kind of like back when we were talking about regular expressions. When computer scientists are using regular expressions, they want them to have lots of very useful common features. But when we're reasoning about what we can do with regular expressions, we want to have as few features as possible. And so we should think about these extra fancier features as just shorthand for various notations in the simpler feature set. From these terms, we can then define what are called the atomic formulas. So an atomic formula is going to be the simplest sort of expression that represents a Boolean, a true or false value. And it's going to be of the form either some term represents the same word as another term, or some term represents a word which is a prefix of another term, or some term represents a word that is the same length as another term. Even though we didn't include equality in our specification of the word structure, model theorists tend to always want to throw it in anyway for free, and there's good reasons why. From here, we then define the set of all formulas recursively. We will define these formulas recursively, starting with the atomic formulas, and then, given two formulas, we can take the and of those two formulas. So this wedge symbol here represents and. It means that F is true and E is true. The way to remember this is it kind of looks like the letter A. And then this V symbol here represents or. And I like to think of that as maybe the R in or. And then we have not F. And these are our Boolean operations. And then we also have quantifiers. We can say that for all words x, some formula is true, or there exists an x such that some formula is true. And we can, in this way, recursively build up the set of all formulas. And there's a great part of a lot of logical texts where they'll say things like, this formula here, F and E, is true if F is true and E is true, and they'll write that out in text, as if somehow the word and has more significance than the symbol and. But there is kind of an important point here. First and foremost, these formulas that we've defined are just strings of symbols. They're just recursively constructed expressions. And what that allows us to do is mathematically analyze individual formulas and also the collection of all formulas, something that we couldn't do if we were trying to define everything in English. Together, we call the set of all formulas constructed in this way the first order logic of the word structure. Compare this to zeroth order logic, where we're not allowed to have variables or quantifiers, but we have everything else. So we can really only say very basic things like the successor A of the empty word is the same length as the successor B of the empty word. It's very hard to say anything particularly meaningful in zeroth order logic. Nonetheless, it is important to study. It's important to establish what the rules are for the basic Boolean connectives prior to studying first order logic. Compare also with what's called second order logic, where variables are allowed to represent not just words, but sets of words, or relations on words, or functions on words, giving us a much more powerful and expressive language. Let's take a look for a moment at a formula in the first order logic of the word structure. This formula is built up recursively out of both the pieces that we've specified in our description of the word structure and also first order logic pieces. We can visualize how these pieces have been put together by looking at an abstract syntax tree for the formula. Here, each node is either a basic piece of the formula or a specification for how we can combine higher nodes to produce a new, larger formula. Having abstract syntax trees makes it easier to formally reason about particular formulas. This formula has two variables. We have x, which is given context by this quantifier here. So this formula actually isn't saying anything about x overall. What it is telling us is something about y. Specifically, for our particular value of y, there's going to exist an x that makes this happen. This variable x is said to be bounded because there's a quantifier for it, and this variable y is said to be free because there is no quantifier for it. And it's because y is a free variable that this formula says something about the word y. I'll give you a moment to try to figure out what it actually says about the word why. So we have two things that we can do with our language. We can make assertions about particular words. This formula here is an assertion that we can make about various words, right? Does a word why satisfy this formula or not? Well, it depends. On the other hand, if we have a formula that has no free variables, like this, we call it a sentence, and it's making an assertion that could either be true or false about the logic. Again, I'll let you try to figure out if this assertion is true or false. Is it true that for any word y, there's going to exist a word x, such that x with an a tacked onto the end is a prefix of y? We defined the theory of the word structure to be the set of true sentences in the first-order logic of the word structure. This includes these sentences here. I'll give you a moment to pause and try to figure out what these sentences are saying about the word logic. So the first sentence says essentially that every word is either empty or has a last letter. The second one says that every word is empty or has a first letter. The third one says that any two words have a greatest common prefix. The fourth one says that every word has a word that's all A's that's the same length as it. And the fifth one says that every word of suitable length has a character at position the length of z. We're very interested in studying this theory of the word structure. Is there an easy way to tell if a particular sentence is true or false? Is there a small set of sentences, a small set of axioms from which all of the true sentences follow? And are there other structures that satisfy this exact same set of true sentences? These are all questions that we can ask and answer about the theory of the word structure. We start our approach with an important fact about the word logic. So given a formula phi in the word logic with free variables x1 through xn, so we notate that phi is saying something about x1 through xn, right? That x1 through xn are the free variables of the formula phi, like this, right? By indicating that phi is a function of x1 through xn that outputs a Boolean. There's going to be a corresponding deterministic finite state automaton, a sub phi, which accepts words w1 through wn, where we kind of tuple them together in the sense of our regular relations and multiple inputs video, if and only if phi is true of those particular words, right? When we plug those words in for x1 through xn, does phi wind up being true of those particular words? In other words, given a formula, we can find a corresponding automaton for that formula. The proof for this is going to be an induction on the construction of the formula phi. We'll show that it's true for the most basic formulas, and then we'll show that if it's true for pieces of a larger formula, then it's also going to be true for that larger formula. And therefore, it's going to be true for all formulas. Of course, this is quite tricky. We've already done something tricky where we've worked out how to deal with formulas that have multiple free variables in them. Normally we wouldn't have to deal with this, right? We could work with formulas that have only one free variable and say that they correspond to an automaton that only accepts one input, which most automata do. But in order to get this proof by induction to work, in the process of constructing a formula with one free variable, we need to construct formulas, intermediate formulas, that have multiple free variables, right? Before we reach the quantifiers that quantify those variables so that they're bounded. And so by being able to reason about what it means to input multiple words into a single automaton, we've already done some of the tricky work of this proof by induction. I'm also going to want to do something else. I'm going to want to relationalize our structure. So our word structure has both relations, right, the prefix and the equal length relations, and also operations, right, the successor A and successor B, right, tack an A onto the end and tack a B onto the end operations. Those are functions, those are operations. And what that means is that when we're doing our recursive construction of a formula, that there's actually two recursions going on. The first recursion, which constructs terms, and then the second recursion, which constructs formulas. But if we relationalize our structure, if we turn our operations into relations, we don't lose any expressive power, but it makes our proof by induction much easier. So what does it mean to relationalize a formula? Well, suppose that we have a formula like this. For every x, x is a prefix of x with an a tacked on to the end. This formula has prefix and successor a going on at the same time, and we don't want that. We want to separate out all of our operations into separate atomic formulas. And we can do that by creating a new variable to represent the successor a of x. For every x, there's going to be some y, which is the successor a of x, such that x is a prefix of y, right? So what we've done here is we've isolated this successor a operation into its own separate atomic formula. And that's what it means to relationalize. Let me show you another example. Let's say I wanted to say that the successor b of the successor a of x is a prefix of y. In this case, I'm going to want to introduce two new variables, one to represent the successor a of x and one to represent the successor b of that. This formula here says the same thing. There is a z and a w, where z is the successor a of x and w is the successor b of that, and w is a prefix of y. So it says the same thing, but we've isolated these successor a's and successor b's into their own separate atomic formulas. What this means is that if we want to prove our theorem for atomic formulas, we only have to consider formulas of the form x is equal to y, x is a prefix or equal to y, x is equal to the successor a of y, or x is equal length to y. And the reason why this process is called relationalization is that we could replace this with a separate relation, right? We could say something like SAXY to mean that the successor a of y is equal to x, or something like that. Instead of having an atomic formula that looks like this. These atomic formulas make up the base case for our theorem, and I'll let you work out what the corresponding automata are for these various formulas. Now we induct on the process of constructing larger formulas out of smaller ones. So here we assume it's true for formulas phi and rho, and then we need to prove that our assertion is true, for instance, for formulas of the form not phi. What does that mean? Well, if we have an automaton corresponding to the formula phi, how do we construct an automaton corresponding to the formula not phi? How do we construct an automaton that accepts all of the tuple words that don't make this true? That don't make this corresponding automaton accept? Well, we're simply complementing a regular language, and we know how to do that from our video on closure properties. Similarly, if we can construct an automaton for the formula phi and an automaton for the formula rho, how do we construct an automaton for the formula phi and rho? Well, this is actually a little bit tricky, because the free variables of phi and the free variables of rho might not actually be the same. What we'll need to do is use our closure under expansion to add on more spaces in case there are free variables that are missing from our automaton for phi because they're not free variables for phi, or if there are free variables that are missing in our automaton for rho because they're not in the formula rho. But we don't need to worry about that particular subtlety. This is essentially just closure under intersection. Phi or rho is closure under union. If we want to prove this for a formula that looks like there exists an x such that phi of x comma maybe a bunch of other free variables, this actually just winds up being closure under projection. And finally, if we have a formula that looks like for all x, phi of x and possibly some other free variables, we're actually, this one's kind of gross. We're going to want to turn this into, it's not the case that there exists an x that makes phi of x comma ... false. Right? Saying that something is true for every x is the same as saying it's not the case that there is a counterexample. So we're going to want to take, anytime we see a formula that looks like this, we're going to want to turn it into something like this, and then use this piece and this piece to turn this formula here into an automaton based on the automaton for our original phi. And that completes our proof. We know that it's true for the basic formulas, and we know that if we have a larger formula that consists of one or more smaller pieces, and it's true for the smaller pieces, then we know that it's true for the larger formula. And so therefore, there's no smallest formula for which it's not true, and therefore it's true for all formulas. What's really interesting is that this fact is true even if we have a formula with no free variables in it. In this case, there's a corresponding automaton that accepts an empty tuple, right? What does it mean to feed in the empty tuple? Well, what does it mean to feed in an arbitrary tuple? It means we take all of our words and we tuple together all of the first characters and tuple together all of the second characters and so on and so forth. Well, if we have no words, we're going to tuple together all of the first characters of no words, and then tuple together all of the second characters of no words, and then tuple together all of the third characters of no words, and so on and so forth until we've reached the maximum length of all of the words. Oh, the maximum length of all of the words is 0. And so we actually don't enter any of these things in at all. We don't enter anything into our automaton. We just see if it accepts or rejects. In other words, is the start state an accept state or a reject state? This becomes even clearer if you follow this construction explicitly for a formula with no free variables and at least one bound variable. For instance, we might have a formula like there exists an x such that phi of x. In this case, we have a bound variable x and no free variables, and by our induction, we've constructed an automaton corresponding to the formula phi of x. That is, an automaton that accepts words x if and only if phi of x is true. Asking if there is an x such that phi of x is true is asking if there's any word that this automaton accepts. In order to construct the automaton for this formula, the projection construction from our closure video takes all of the edges of the automaton corresponding to phi of x and causes them to have a label which is a tuple of 0 elements. Unfortunately then, this automaton winds up having a whole bunch of edges whose labels are entirely octothorpes, specifically 0 octothorpes, but there are 0 letters, so they are entirely octothorpes. And so what this means is that we need to unwind those edges. We need to trace everything back along those edges, and what that winds up doing is it winds up unwinding the entire automaton back to the start, and if there were any nodes that were accept nodes, those get unwound via the construction back to the start state. Now we have our automaton corresponding to this formula, and we simply check in order to determine if this formula is true. Did we actually unwind any accept states to the start state? Did we make the start state an accept state or not? Effectively determining if there were any accept states reachable in the automaton for our smaller formula phi of x. Taking a step back, what we've done is we've worked out a way to take a formula with no free variables in it and determine whether or not that formula is true or false in the word logic by simply turning it into an automaton and checking to see if the automaton that we've constructed recursively it has its start state as an accept state or not. Another thing that we've shown is that our word logic is at most as expressive as the regular languages. That is, that there are no languages that aren't regular, that are beyond the regular languages, that we can define using formulas in this particular language. But can every regular language be recognized by a formula in the word logic? In other words, is there a way of formulating finite state automata in this particular language? The answer is yes, and we're going to need some notational shorthand in order to make this clear. Unfortunately, our logic prohibits us from talking about natural numbers, but that's okay. We can still talk about the lengths of words. I'm going to use the length of w to indicate the word which is equal length to w, which consists entirely of a's. We saw before that we can describe when this happens in our particular logic, and all we need to do if we want to say something about the length of w, all we need to do is say that there exists a z which is the length of w, that is this word, and z has the properties that we want to say that the length of w has. Essentially the same as our relationalization construction. I'm also going to want to define the shorthand w brackets v. We want this to indicate the character of w at the position given by the length of v. And so we're going to define this as a if the prefix of w of length, the length of v plus 1, in other words, the successor a of the length of v, ends with an a, it's going to be b if this ends with a b, and it's going to be epsilon if w is shorter than v, if w is too short. And again, we've seen how we can define this. Just for clarity, I want w of the empty word to be the first character of w. That's why I've added this plus 1 here. And w of the length of w minus 1, which this is actually kind of a sensible thing to say, at least if w isn't the empty word, because we can find a word that's all a's that's the same length as w, and we can find a word that's all a's whose successor a is that. And so this is going to be the last character of w. I've chosen this to agree with computer science notation, where the 0th element of a string is its first character, and the length of the string minus 1th character is the last character of the string. It has to be off in one direction, and I've chosen to shift everything in the direction that makes sense if you've been doing a bunch of computer science string indexing. And again, if we make certain assertions about the vth character of w, we can unwind those, unpack those to a formula that doesn't involve assertions about the vth character of w. So let's build our automaton. Figuring out how to build things in particular logics is tons of fun. And if you want to pause this video and try to work out some of this for yourself, I wouldn't blame you. This is tons of fun stuff to do. So given a particular deterministic finite state automaton, and let's assume still that sigma is just the 2-letter alphabet AB, we would like to encode a run of this automaton. Now, the thing about runs of automata, so the input to this automaton is going to be a word in sigma, right? It's going to be a sequence of A's and B's. And a run of this automaton is going to be a word on elements of Q. It's going to be a sequence of states. And the problem is there might be more than two states. If there were just two states, we could have our two letters A and B, which we're allowed to talk about in our logic because we're doing the word logic over sigma. If there's only two states, we could just say A is one of the states and B is the other state, and our sequence of A's and B's is going to encode our run. The problem is Q is probably going to consist of more than two states. So how can we encode more than two states using just words on A and B? Well, we're going to use a separate variable for each state. And in positions where this variable is an A, that's going to indicate that we're in that state, and in positions where this variable is a B, that's going to indicate that we're not in that state. So if we have a run that starts off in state 0, and then we read an A and it winds up in state 1, we read a B, it stays in state 1, we read an A, it winds up in state 0, we read a B, it winds up in state 2, we read an A, it stays in state 2. If we want to represent this run for this particular input, we're going to have to shift it over half a unit, and it's going to look something like this. We'll have our original word W, which is going to be A, B, A, B, A, and then we'll have our three words indicating our states that will look like, to indicate that we start off in state 0, we're going to put an A in the first place in x0 and B's elsewhere. To indicate that we're in state 1 in the next place, we're going to put an A in state 1 and B's elsewhere. To indicate that we're still in state 1, we still have an A in x1. To indicate state 0, we put an A here. To indicate that we're in state 2, we put an A in state 2, lining up with this last A here, and B's elsewhere. And then to indicate that we're in state 2 at the end, we put an A in state 2 and B's elsewhere. And so instead of having our triangles look like this, we have our triangles look like that. That's kind of how we've decided to shift everything over. And so using this construction, we're able to encode the sequence of states, which there might be more than two of. And so all we have to do to construct a formula out of our automaton, right? Our goal is to construct a formula that corresponds to whether or not this word gets accepted by this automaton. All we have to do is ask, does there exist an x0, an x1, and an x2 such that this is a valid representation of a run, that is, there's only one A in each position, and the start state is correct and the end state is correct. So again, if you want to pause and try to construct that formula, I encourage you to do so. So let's say that we have a particular automaton that we want to encode as a formula. Well, we're going to say that a word is accepted if there exist words x0, x1, and x2 such that each of these words is equal length to a successor of W. It doesn't matter which one, we just care about the length. But remember that our run is going to be one letter longer than the input word. It then also needs to be the case that for any y, which is a prefix of W, and we're going to think of this as a length, any length that's less than or equal to W, the character of that position, in x0 being A, implies that the character at that position for x1 is equal to B, and the character at that position in x2 is equal to B. On the other hand, if the character at position y in x1 is equal to A, then the character at position y in x2 is equal to B. On the other hand, if the character at position y in x1 is equal to A, then the character at position y in x2 is equal to B. On the other hand, if the character at position y in x1 is equal to A, then the character at position y in x2 is equal to B. On the other hand, if the character at position y in x1 is equal to A, then the character at position y in x2 is equal to B. the character of x0 at position y is equal to b, and the character of x2 at position y is equal to b, and the same for x2. If the character at position y of x2 is equal to a, then the character at position y of x0 and x1 are going to be b's. And this is actually going to be an if and only if. We want to make sure that exactly one of the characters at position y of each of our x's is equal to a. So this sets up the basic premise that x0, x1, and x2 together represent a run of our automaton in this representation that we've picked. But we want to make sure that they represent a run of our specific automaton, that they're a valid run. And so, I hope you don't mind if I erase, because I've run out of room. We're also going to want to say that because 0 is, whoops, forgot to label that, because 0 is a start state, we want it to be the case that x0 of epsilon, the first character of x0, is going to be a, and for all y which is a strict prefix of w, and we can use this notation, this just means that y is a prefix of w and y is not equal to w, so you could expand this out if you needed to. So for any, again we want to think of y as a length, for any length that's before the end of w, it needs to be the case that if x0 of y is equal to a, so if at time y we're in state 0, and we read in the character a, then at time y plus 1 we're in state 1. So at time y plus 1, at the next position, x1 is going to be the word that has the a. On the other hand, if x0 of y is equal to a, so if at time y we're in state x0 and w of y, and we read a b, then we're going to wind up in state 2 next. So x2 of say gets the a. And so on and so forth. We just and together a whole bunch of clauses like this that correspond to every particular edge of this diagram. So for instance, if x1 of y is equal to a, so if we're in a state 1 at time y, and w of y is equal to b, then x1 of y is going to equal a. X1 of the successor of y is going to equal a. That is, the state that we're in at the next moment of time is going to be equal to a. And then finally, oh, I forgot to include final state. Let's say that 1 is a final state. And then finally, x1 of w is equal to a. And we could, if there were multiple final states, let's make 2 be a final state as well. Then we want to say that x1 of w is equal to a, or x2 of w is equal to a. And because x1 and x2 are 1 unit longer than w, this is going to refer to their last character. So either the last character of x1 is equal to a, or the last character of x2 is equal to a. And so if we expand out this bracket notation, we wind up getting this really long and complicated formula representing this finite state automaton here. And the generalization of this is actually pretty straightforward. If we have any deterministic finite state automaton, we just say that there exists a word for each state. We specify that those words together form a representation of a run of an automaton reading the word w. And then we specify that the start state begins with an a, And then we have some sort of complicated formula here that specifies that if we're in a particular state at a particular time and we read a particular character, then we wind up in a particular state at the next time. And then finally, we specify that we're at the end, we're in one of the except states. And so this gives us a procedure for turning a deterministic finite state automaton into a formula in the word logic. As such, we can represent any regular language in the word logic as the set of all words x such that phi of x. This is going to be a regular language over sigma, sigma being the letters a and b. We just have the set of all words that satisfy a particular formula. This is going to be a regular language, and all regular languages are in this format, that there's some phi, there's some formula in our word logic that represents that regular set. If you're concerned about the case where sigma has more than 2 letters, we can use the same sort of representation that we did for our states, because the states were words on more than 2 letters. We can use that same sort of representation to represent input words on more than 2 letters. And the same sort of thing applies, but you have to worry about encodings. And it's a real nuisance, but you can do it. And this proof actually winds up falling apart completely. We really genuinely need A's and B's. We need at least 2 separate characters to do this sort of construction. This fact that the word logic is expressively equivalent to finite state automata is actually not true in the case where sigma has just 1 letter. But anyway, this is the really exciting thing about regular languages. This is the thing that got me interested in these finite state automata in the first place, is the fact that really what you're doing when you're talking about regular languages is you're talking about the expressivity of this particular logic. And I find it really exciting and interesting to ask questions about what can we say in a particular logic, and how hard is it to say those things, and how can we determine what's true, things like that about particular logics. And having this really nice correspondence between formulas in this, admittedly it's a little bit of a, I mean, it's a bit of a logic. There's, several things going on. There's equal length, there's prefix. It's not the most natural logic in the world, but it's a pretty natural logic when it comes to talking about words. But there's this really nice logic that winds up corresponding exactly with the finite state automata. In the next video, I'd like to show you a slightly simpler language that winds up corresponding through a translation process to the regular languages. So let me know if you have any questions in the comments, and I hope to see you then.